Hi there. Okay, let's get started into our lab 3. So it's going to be on planetary geology. So let's see here. Okay, this one, lab 5. This is going to be our lab 3. It's going to be a non-write-up lab. So again, similar to the first lab, you don't have to type it. If you want, you can write it. And you don't need the whole cover page procedure, all that stuff. So we start with seismology. So some interesting topics we're going to see here. Okay, Earth's interior. By comparing the density of rocks on the surface of the Earth to the planet's overall density, we can tell that the interior must be more dense. So density, in my opinion, is one of the most important quantities to describe something. So it tells you how much mass is compacted into a certain volume, all right? So one can begin studying the geology of the Earth by noting that it must be much denser at the core than near the surface. Rocks on the surface of the Earth have densities of about 2 grams per cubic centimeter. So that's the density of the rocks at the surface of the Earth. They're about 3 grams per cubic centimeter. But when we calculate the average density of the Earth by taking its mass, by multiplying by the volume of the Earth, this is the equation for the volume of a sphere. So if you do the volume of the Earth and then you take its mass, you divide them, you get 5.5 grams per cubic centimeter. So you see, you could tell that the overall density of the Earth is denser than the density of the rocks at the surface. So that means the inside of the Earth must be denser. It must be keep getting denser and denser as you go to the core of the Earth. So it says, this is because of two factors. The materials near the center of the Earth have an inherently higher density than the material near the crust. Yeah, you see, kind of like I said, the denser material sinks down into the core of the Earth. And this is also similar for other planets. So we would expect that the denser materials are in the core. Then the second one is the weight of the overlying layers compresses the material below it into higher densities. That means that also causes the density of the core to be higher because you got all the weight of the object on top of it pressing down on it, so it compresses it into a smaller volume. By doing that, it makes the density even higher. This separation of materials into different densities is known as differentiation. So, for example, they give you materials here and their densities. Lead is 11.3 gram per cubic centimeter. Iron is 7.8 gram per cubic centimeter. And then you got the densities of some of the planets. Earth is the densest planet with a density of 5.5 gram per cubic centimeter. Mercury is a close next, 5.4. Venus is next, Mars is less, and then the moon is even less. So the less the density of the planet, that means that planet is more dominated by rocky material, you see. Like the moon is probably more rocks and granite or whatever. You see here, we can see that granite and aluminum have a density of 2.7. That means the moon is mostly made up of those kind of materials like granite, rocks, maybe slightly denser. Mars probably has some more stuff in its interior, but not that much. But Mercury and Venus, they're more like Earth's. So we would expect them to have a core of iron in there. Pluto has a density of 2 grams. per cubic centimeter. That means it's probably just a little bit more, or twice more dense than water. So that means it's primarily composed of water and ice and some other heavier material, but not that much. Okay. So seismic waves. Waves generated by earthquakes travel through the earth and carry information about the interior to the surface. We can learn about the interior of the earth by studying the transmission of seismic waves through the earth. These waves are most often produced by earthquakes, but can also be caused by impacts or explosions. Seismologists identify two different types of relevant seismic waves. P waves, pressure or compression wave. This is a pressure or a compression wave, are longitudinal waves, meaning that the medium through which the wave travels moves back and forth in the same direction that the wave is traveling. S waves are transverse waves, meaning that the medium moves perpendicular to the wave's direction of travel. So S is perpendicular and P waves are longitudinal, which means it's parallel. So let's look at a simulation here. This would be an S wave. You see how the material goes up and down, and the wave travels from left to right and back and forth and back and forth. But the material is going perpendicular to it, up and down. You see? So if a S wave is coming to your house would shake up and down as the earthquake is passing by you. I believe S waves would do more damage to the house, to buildings. P waves is this way. You see? Then the house would shake left and right like this. So this is a longitudinal wave. The objects are going back and forth as the wave is traveling from left to right. In other words, they're oscillating in the same direction, parallel. I like doing that. Yeah, P waves would not do as much damage to buildings as much as the S wave. Okay, next. So because P waves and S waves travel differently through the interior of the Earth, detecting both types is important for understanding the interior. When an earthquake occurs, both P and S waves propagate through the Earth. Both types of waves may undergo reflection and refraction. That means bending. Okay, so they can reflect, refract, and bend, right, at the boundaries of layers that have different densities. Both waves also refract as they travel through the Earth. This is due to the increase in density with depth. So in general, P waves move faster than S waves. So that's one thing to note. P, and you can kind of remember P with the word primary and S with the word secondary. So the P wave is the one that's going to reach your house first. That's the primary wave. Then a little bit time later, the S wave, the secondary wave, is going to reach you, and that's going to shake you up and down, whereas the P wave is going to shake you left and right. So another difference between the two is that the pressure or compression waves can travel through either solids or liquids. So that means these guys can travel through solids or liquids, both. And then the S wave, whereas the shear waves cannot propagate through liquids. So remember it this way, S for solid. So S waves cannot travel through solid, cannot, okay? So they are secondary, that means they're slower, and they also cannot travel through, hold on, shear waves cannot propagate through liquids. Oh, I think I said it wrong. No, hold on. S is the secondary. S waves means they can only travel through solids. Oh, I said it wrong. Yes, yes. So shear waves cannot propagate through liquids, which means they can only travel through solids. Yes, now I said it correctly. So S wave is secondary and they can only travel through solids. Seismograms are collected from all over the world when earthquakes occur. They allow us to study whether or not both types of waves have been detected, and they also reveal their relative arrival times. So regions within the Earth. The interior of the Earth is divided into 4 concentric layers: the crust, the mantle, the outer or liquid core, and the inner or solid core. So from P and S wave measurements, as well as other measurements, seismologists can identify 4 distinct regions of the Earth's interior: solid inner core, a hot nickel and iron region extending from the center of the Earth to about 1,200 kilometers. Liquid outer core, a liquid nickel and iron region that extends from 1,200 to 3,500. Mantle, a lower temperature region primarily composed of silicates, which are lower in density than nickel and iron. So silicate means anything that has silicon and oxide. Silicon and oxide, that's a silicate. And it's kind of like where we get our sand from. That is actually a silicate. It's composed of silicon bonded with oxygen, and that's called a silicate. The mantle extends halfway through the Earth, almost to the Earth's surface. The crust, the lower density brittle outer layers of the Earth, is 20 to 70 kilometers thick. The crust is almost composed mainly of silicates and, of course, rock. So the crust, the percentage of the mass. So the crust, that means the crust comprises 0.5% of the mass of the Earth, and its average temperature is 500 Kelvin. That's still warmer than room temperature. Room temperature is 300 Kelvin. That's the temperature we live at on the surface of the Earth, is about 300 Kelvin. So that's 200 degrees above room temperature. So that means if you dig into the crust, your metals will already start melting. You can't dig too much because the temperature is going up by 200 Kelvin. The average density of the crust is 2.5 gram per cubic centimeter. The mantle comprises 67% of the mass of the Earth. The average temperature, 3,000 Kelvin. And then the density is starting to go up, right? 4.5. The outer core, 30.8. The temperature is going up. The density is going up. By the time you get to the inner core, the density is 12.9. So if you kind of average all these densities, then you get the total density of the Earth, which was, what did we say it was? 5.5. 5.5 is the average density of the Earth. So Earth Explorer, let's see here. Let's see, show labels. Yeah, so the inner core, this is the solid portion. So this kind of helps give a picture to this. And then you got the outer core, okay? And then this is the part, the orange is the part that's liquid, okay? And then you got here is solid. So it's like, I kind of remember the movie, when you go to the center of the Earth and there's sea there, the Journey to the Center of the Earth movie, right? In a sense, that movie is kind of true. If you were to go all the way to the center of the Earth right there, this part would be liquid, and you could almost like get a boat and ride on that. Of course, if you can withstand the temperatures. But there is a water, there is a liquid there. So in a sense, it is kind of not that wrong. Then you get here. Oh, okay. So it gives you the whole thing here. Oh, so if I click on this, it will give me all the So if I go like that, it gives you the whole thing about the temperature of each one, the S wave velocity. See the S wave velocity, the P wave velocity. So the S wave velocity, or as you're going down, the velocities keep changing, you see? So you can kind of like click here. The density is 3.94 at that point. The pressure is 20.28 gigapascals. Gravity is 18.9. So the gravity at the surface of the Earth is what? It should be 9.8 at the surface of the Earth. That's the acceleration due to gravity. Now, as you're going down, the gravity is increasing, the temperature is increasing. And notice the S wave velocity and the P wave velocity is also slowly increasing as I go down. So like that, then like that. Oh, the S wave velocity is negative. That's weird. The P wave velocity, then 0.48, like that. So the P waves are always faster, and the temperature keeps increasing. Temperature keeps increasing. Now, if I go here, S wave velocity is 0. What do you notice there? You see, the gravity, at that point, the gravity is 9 point, so right there. You see right there, somewhere there? Yeah, somewhere there, you would weigh the same thing that you do at the surface of the Earth, because the gravity is back to 9.8. Yeah, right around there. So if you were to go down, essentially into the center of the Earth, your weight would increase, increase, increase until you reach that point, right at that point. Then at that point, the gravity would be 9.8. So you would weigh the same thing that you do on Earth. But of course, the temperature is very hot. Now, what do you notice about the S wave? Remember, we said S wave can only travel through solids. So the velocity in the liquid core is 0, you see? But the P wave is still traveling through the liquid portion. Then you go like that, you go like that. Okay, then the S wave is back on. But the problem is, if it can't penetrate the liquid core, then what good is it that it can travel through the inner core? You won't even get there, right? So now the one thing you notice about the temperature is it's still going up, and the density is going really high. So by the time you get to the center, the density is 13.1 gram per cubic centimeter, and the pressure is very, very high, 370 gigapascal. What's the pressure at the surface of the Earth? Okay, it's right about, let's see here. Yeah, if I go to the surface, yeah, about 1.31 gigapascal right there. That's the pressure that we feel at atmospheric sea level pressure. So of course, as you go down, the pressure is going to increase until you get to 365 times the pressure at sea level. So those are kind of interesting things you can see as you are pressing this. Earth interior exercise. Okay, this is the first exercise. Okay, so this one, since there's only 3 questions, take a picture of each one. Take a picture of each of the questions and what answer you got. What is the temperature at the center of the Earth? Okay, so what would that be? So then you would go, you can't really use this number, the inner core, 5,700. You can't really use that because that's the average temperature of the inner core, you see, but it varies. So if I were to find out the exact center of the Earth, then I would have to go click. So like go click right there at the center. And whatever answer that you get, 5987, right? Does it show? So then you take a picture of that. So if answering these questions requires you to go and do something here, then you also need to document that. So you got to go here and go and then click. Yeah, it looks like it's 5987, but each person might get something different. 5974 I'm getting now. So take a picture of also this picture and then showing the right side, 5974. Notice that that's more than the average temperature of the inner core, because that's only the average, you see. So you should get something higher than that. And then once you put that answer here, let's say if I were to put it, okay, then you would take a picture of that. And then you go to question 2. Approximately how thick is the mantle in kilometers? So that means they want to know from the mantle from here all the way to here. What is that? So how would you do that? Can you? Well, the information here you can't use. Let's see. Maybe you can go take a picture of that like this, right? And then showing the radius. Let's see here, right there. And then go all the way to here, show the radius, and then subtract them. You see? Or you could use the depth. The depth is measuring from the top to the where you click, right? And the radius is measuring from the center to where you click. But if I want to know the thickness of something from here to here, right? Then you can do, if I want to know the thickness of something from here to here, you could either use the radius of that point and the radius of that point and subtract them, or you could use the depth and subtract them. I think you should get the same thing. So then you have 2 pictures to take over there, one here, and then one all the way out here. Try not to include the crust, like right there, maybe a little below the crust. You see? Yeah. So then you were to subtract those 2, that would give you the mantle. And then you would put the answer here, submit. So how many pictures would that be? 2 for these, showing the radius or the depth. And then take the difference and put it here. And then click submit, and then the answer. So basically 1 of this and then 2 of those. And then question 3. Approximately how much mass is in the liquid outer core? So how would you do that one? The liquid outer core. That one we might just be able to use this one. The outer core, it says 30.8% of the mass of the Earth. I think that's the best way to do that. Use this and then find online what the mass of the Earth is. So just do a Google search. So do a Google search for that one, what the total mass of the Earth is, and then take a picture of your Google search. So the number that came out. So do a Google search, what is the mass of the Earth? Take a picture of that. Then use this percentage. Take a picture of this part, like this, right? Showing that the percent mass by breakdown, you see? So then argue that if I want to find the mass of the outer core, I'm going to take 30.8% of whatever search you did, the mass of the Earth on Google. Then multiply them, and then put the answer here. Okay, so for that one, show your work. I know it's a simple work to show, but just show the math. So imagine that someone else is reading it, an audience that's not me. So you want to be as thorough as possible, showing how you are getting these things. So say, okay, I'm going to take this percent, show them the percentage, show what the mass of the Earth is, then show how I'm getting the mass of the Earth from that. So it's probably just a one-step thing where you can show how to get the mass of just the liquid core, then put it in here, and then press submit, of course, and then show that your answer was correct. Okay, then the next exercise. So the simulation allows the measure of seismic waves on an unexplored planet in order to determine the structure of the interior. So click and drag the probes around the planet to prepare them to detect the S waves. Then click the Make Waves button to create a burst of seismic waves from the top of the planet. So what they're going to do is simulate, let's say there's an earthquake that happens here. As that earthquake happens, it creates S and P waves that go through, and then you have some random seismographs. So you see this represents the angle. So if I put here, that means the seismograph is 180 degrees from where the earthquake is happening. You see? So if the earthquake is happening there, it's opposite. So it's 180 degrees, you see? If I put it here, it's 150 degrees. You see, like that. So it's like this, like that. That's 150 degrees. So then I could take this, put it at a 60 degree. Okay, then I could put this at 90 degrees. You could do something like that. Okay. So it says here, then click the Make Waves button to create a burst of seismic waves from the top of the planet. As the probes detect the S waves from these bursts, their data will appear in the plot of time in seconds versus delta. The delta is the angle. Press the Next Page button to use these data to infer whether the planet has a liquid region. Press the Help button for the help window. So Make Waves. So only two of them detected the S wave. So there must be, so now let's see here. Oh, okay. So now what we have to do is we have to match the data that we got. So you see, we got one data at the 60 degree mark. That means the 60 degree is this one. Yeah, right here. This guy detected an S wave in about almost 300 seconds. You see, it took it 300 seconds. So what would that be? About 5 minutes to detect the S wave. So that means the S wave went like this, bent around, and then traveled. So since this is solid, the S wave went from here. It could travel like this, bends. Remember, the velocity keeps changing. So because the velocity of the S wave is changing, it's bending constantly. Bending, and then going there. And it's taking it around 5 minutes, you see. 300 seconds is equivalent to 5 minutes. It's taking 5 minutes to get there. Then this guy, the 90-minute guy, the 90-degree guy, is going like this, and then bending, and then it's going there. And then it's taking it around 400 seconds. So that's about 7 minutes. 7 minutes for this detector to observe that earthquake. This guy is never observing it. Nothing. No observation. So what does that mean? Well, there must be a huge liquid core here, you see. So let's see here. If I increase the liquid core, also I got to play around with the S wave velocity, the average S wave velocity. So the average S wave velocity as it's going from here to here, you see. So we know that this guy observed it. So the liquid core can't be this big. You see what I mean? Because then if the liquid core was this big, neither this seismograph nor that seismograph would have observed it. Only these seismographs from here to here would have observed it. So the liquid core can't be that big. So it's probably like this, right? It can't be too much bigger than that, because this guy observed it and then that guy observed it, you see? So now what this is telling you here is that any seismographs from here to here wouldn't be able to observe the S wave, you see, from here to here. So then the S wave velocity, now I got to play around with it. Does it fit that data? Yeah, right there. So that means the average S wave velocity while it's traveling through this medium is the average S wave velocity is 5.4 kilometers per second. The core radius, we can't really tell what it is, because if I make the core radius bigger, it still fits the data. So how big can it be? It can possibly be this big. You see? But that gives me a lot of room for error for the core radius, right? So it could be this small or it could be this big, you see? But at least the S wave velocity, I have it down very for sure. So I can say for sure the S wave velocity has an average velocity of 5.4, but the core radius can be as small as 0 or as big as 1,000 something. So where should I have put my third seismograph then? Maybe I should have put it at more. Well, the best thing to do is have more seismographs, of course. Have one here, have one here, have one here, and have one here, so on, right? But if I'm only have 3 seismographs around the Earth, I think 180 degrees was not advantageous for me, because 184 doesn't give me too much information. Probably I need one at 60, 90, and then maybe 150 would have been good. Now let's repeat. Okay. It's probably still not that. Well, the 60 guy is getting it and the 90 guy is getting it. Let's see here. Maybe keep moving it. Ah, you see that? Now the third guy got it. This guy got it at 100 and something degrees. Now, so maybe what I should do is keep moving it back down until I don't get it. Ooh, and go down a little bit more. I like the fact that it's keeping the earlier ones. Oh. Oh, okay, okay. So they see now it's not getting it. So right around there. I like this. I like this one. This is how we find out the size of the liquid core. Oh, I got it. So let's zoom in on that. Okay, maybe one more. Okay, I think that was the very last edge that got it. Okay, so then I'm gonna go, let's zoom out. Okay, with the velocity of 5.4, let me see, I'm still feeling all the data. Now let's go to core radius. So now I'm gonna zoom in. Oh, zoom out a bit. Okay, so now I can play around with the S wave velocity a little bit more. I also get a better measurement of the S wave now. See, right. Okay, about 5.4 is still the average, but it looks like it should be 5.4 something, 5.45 or something like that. Like I say, either one, 5.4 or 5.5. Now, what's the size of the core? What I'm going to do is say, make the core go bigger until the last seismograph to get the S wave is that guy right there. You see? So that means any seismograph from here to here would not receive the earthquake from that portion. You see? So I think that's the, what happened to the graph? Oh, I think when I, hold on. Let's see, 5.4. I think this one is a better fit right there, 5.5. So now let's go bigger, 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 right there. Okay, so now, okay, so now you could take the picture of that, showing all the seismographs that you have right here. And it shows the angle of the first one is 60 degrees, 90 degrees, and all the other ones you used. Like that, until you got the last one is about 135 degrees. And then it shows the core radius is 400, and that's the core, the liquid core. Now the solid core is going to be inside of it, but we're focusing on the liquid core. You see, so the solid is going to be right there. So this one actually has a small liquid core, this planet. It's not that big. So does the unknown planet have a liquid region in its interior? You can say yes. Correct. Okay, now this one, you again take a picture of each one. This one is just a yes or no, so nothing else to show for that. So yes. What is the radius in kilometers of the liquid region? So then you would, that's where this picture would come in. You would show this picture showing the S wave velocity and showing the liquid core, and then actually showing the size of the liquid core. Really nice setup here. And then submit your answer. Then the question 3, what is the S wave velocity in the planet's mantle? Well, it's all answered by that picture. You see, so then you would show a picture of each one and then go on to the next one. So let me show you a little video that I found about this, because this is really cool how this technology actually works. Short video. These are called travel time curves.
The travel time curve is a time versus distance graph of the time that it takes for seismic waves to travel from the hypocenter of an earthquake or other ground shaking event to seismograph stations varying distances away. They're constructed by analyzing thousands of earthquakes from hundreds of seismograph stations around the world, and they're used by seismologists to quickly locate earthquakes. But how are they determined? To explain, we'll use a simple graph of P, S, and surface wave arrival times while exaggerating the relative motion as the waves hit the buildings, representing seismic stations.
You can see here,
we show an earthquake near the top of the globe and graph the seismic wave arrival times to recording stations at increasing distances from the hypocenter, which is the location below the surface.
So you can see here, they're doing a little bit more than what we did. They're focusing on the P wave, which is the red one. We didn't do that one. We just mainly focused on S wave. So they're focusing on the P wave and the S wave. So you see the primary wave arrives first, then the S wave, and then they're also talking about surface waves, the waves that you get along the surface, you see? So those might arrive first. Even the surface wave might arrive before the primary, just depends. But here it's showing that the surface wave is the lagging behind the secondary and the primary. See, it's lagging behind. So they're making 3 graphs, whereas we just made, we focused just on the S wave. So we were in that lab, we were only focusing on trying to find the size of the liquid core. And that's all you need is the S waves for that. But if you want to find out where exactly the earthquake took place, you need to analyze all 3 of them, the surface, the S, and the P, right? Okay, now let's go.
Where the earthquake actually occurred. The y-axis shows distance from the earthquake, and the x-axis shows the elapsed time since the event. The seismograms record the arrivals of the compressional P, the shearing S, and the rolling surface waves. These motions are also reflected in the motions of the buildings. Seismic waves travel at different rates, so the farther a seismic station is from an earthquake, the farther apart the P, S, and surface wave arrival times will be. Here, we show only direct P and S wave paths through the mantle and crust. The final image of this animation will show more of the complexity within the Earth as the waves are reflected, refracted, and damped due to...
So now look at how complex this is when you really want to analyze, because the waves go, they bend inside the liquid core, then they bend out coming here, then they might reflect back. If it's a P wave, it might do all of these. P waves can travel to the liquid core, so they might do all kinds of crazy things, right? And then they reflect. So you might get a seismic station here reading it, then it goes back, and then another station here reads it. You see, so all kinds of complexities occur.
The changes at depth. Connecting the waves through the stack of seismograms creates the travel time curves that can be used to locate earthquakes. Simply stated, the time difference between the arrival of the P wave and the arrival of the S wave can be used to measure the distance from the seismometer to the epicenter. This iris poster of the 1994 Northridge, California earthquake reveals more of the complexity beyond just P, S, and surface waves. That earthquake killed 51 people, caused over $20 billion in damage, and raised the Santa Susana Mountains north of Los Angeles by 70 centimeters, or 28 inches. It also created seismic waves that ricocheted throughout the Earth's interior and were recorded at geophysical observatories around the world. The paths of some of those seismic waves and the ground motion that they caused are shown on the globe.
This is the Northridge earthquake that I happened to live through. Just a nightmare. So they're showing how the waves spread out specifically for the Northridge earthquake. So it's a nice video that kind of is similar to what we are doing here. Okay, so now I think that's it for that. So we can now go to the okay, let's go to planetary geology. So we did now let's go to supporting evidence. So although seismic waves are the most direct measure of the interior of the Earth, the surface carries other clues about the structure of the interior. Volcanoes are one observable effect of the heat still trapped in the Earth's interior. The interior of the Earth still retains much of the heat of its formation. Energy slowly being transported to the surface through conduction and convection as the Earth cools off. This transported energy has several measurable effects at the surface, such as the generation of the Earth's magnetic field, plate tectonics, earthquakes, and volcanoes. In other words, it's saying all of these phenomena that we have, plate tectonics, earthquakes, volcanoes, and magnetic field, is a leftover of the original energy that the Earth had when it collapsed and formed into a planet. So that heat that originally the Earth was very hot, hotter than it is now, that heat that it still has is causing all of these phenomena. Convection in the outer core is responsible for the Earth's magnetic field. You see? So as these convection currents are happening in the outer core of the Earth, in the liquid outer core that we were just talking about, they cause the magnetic field of the Earth. And that really helps us because it helps protect us from the dangerous solar winds, solar particles that are coming toward us. So the adjacent image illustrates convection currents in the outer liquid core that transports thermal energy towards the surface. This circulation of liquid iron nickel alloys is thought to be responsible for the Earth's magnetic field. This process is referred to as the Dynamo Effect. You may wonder how the Earth's hot inner core is solid while the relatively cooler outer core is liquid. Remember that the particular phase that matter is in depends both on its temperature and pressure. The material in the inner core is much higher pressure than that of the outer core, and thus has a much higher melting point. So the liquid core, which is in the solid core, which is inside of the liquid core, you would think would be even more melted because it's hotter. But because of the higher pressure, it changes back to solid because its melting point rises. You see, so that's what turns it back to a solid. Continental drift, also known as plate tectonics. Convection currents in the mantle push pieces of the crust around like plates. This process is called plate tectonics. Although the mantle is composed of solid material, it is in a plastic state that is capable of flowing when under stress. Although it says the mantle is composed of solid, but it is in a plastic state that is capable of flowing. So we say that it is solid, but it is a flowing type of solid. That's the mantle. And that's what we see when the mantle spews out of volcanoes. We're seeing this lava flow, right? Even though it's flowing, we still call it a solid, the lava that's coming out of the volcano. And as soon as it gets cold, it just solidifies, and we see the true solid nature of the lava. When the hot plumes of mantle material rise to the surface, they push against the crust and create slow convection currents. The process whereby pieces of crust are shifted by mantle currents is known as plate tectonics. So this simulation, let's go a little bit, shows the continental drift over the ages. Use the slider to set up an initial age of the simulation. Press the start button to view the simulation. So you can kind of see here, oops, you can stop it at any point. So you see originally you have everything is kind of like almost together. That's called Pangea, when all the continents were together. Then the continents broke apart. So you can see now Africa and South America were together with North America and Asia. And then this is what became modern day India. And Antarctica, and Australia. So then when I drag it, this is 200 million years ago. Then when I go like this, already South America has split from North America, and the splitting of through Africa is starting to occur. And the Australia is beginning to split from Antarctica. So now, okay, now you see this one, the split has really happened here, South America and Africa. This is still kind of together, but India is way apart from Africa. Ooh, I like that. All of a sudden, a shift of direction. See this one was going that way, then it all of a sudden turned this way. Then Alaska is separated. Oh, now notice what's happening here. This one, Central America is beginning to form. See right here. So right now, this is like North and Central, right, together. And this is South America. So now Central America is starting to form. And India is starting to get pushed towards the Asia. That's where you get these big mountain ranges, the San Andreas, not San Andreas, Mount Everest, right here, Mount Everest. This guy's pushing up against that and pushing it upwards and forming mountain ranges. And then Central America is going to eventually close with South America. This is 9 million years ago. And finally, 3 million years ago, and then present. So you see now you've got the whole North America, Central America, South America, Africa. So interesting how that happened, you know. So this was proposed by 1912 by Alfred Wegener. He suggested that 250 million years ago, all of the continents were part of one giant continent, which he called Pangaea, meaning all the land. Mantle convection then caused slow continental drift, until the present arrangement of continents. Plate tectonics, rift zones and subduction zones are indicators of plate tectonics and of interior heat. So you see here, this is a rift, meaning two plates are getting separated. So when the convection under the Earth pushes this up, these two plates start moving this way, and a rift is created here. And then this plate comes and then subducts under this one. So this plate comes and goes under, subducts under the other of the continental plate, and then hot material rises into volcanoes, you see, right here. As this plate is going under, this hot material here is going upwelling, and then you expect there to be volcanoes where one plate is going underneath the other one. And then same thing here on the other side, you see. So regions where two plates are separating are called rift zones. Molten rock rises to fill the gap and then solidifies. About 2 square kilometers are added to the Earth each year. A rate sufficient to replace the entire oceanic crust in about 100 million years. That means our Earth keeps replenishing its crust every 100 million years, right? So that's very interesting. So therefore, you don't expect to find too many old rocks older than 100 million years if you were to go search under the ocean rocks, because it's renewing itself. It's kind of almost like our skin, which renews itself every day. We shed it, and then it renews itself eventually over time. So rift zones are commonly found in the oceans and thus cause the oceans to grow. There is one substantial exception in Central Africa. Regions where one plate is being forced beneath another are known as subduction zones. The amount of crust created at rift zones roughly equals the amount of destroyed at subduction zones. So you're creating at rift zones, and then you're destroying them underneath when you're getting to the subduction zone. Volcanoes are one way of marking subduction zone and the boundaries between tectonic plates. The Puro cone, part of the Kilauea volcano of the Hawaiian Islands. When a plate is subducted, it is forced downward into a region of higher temperature and pressure, and it will ultimately melt a few hundred kilometers beneath the surface. You see that? You see what's happening? So the plate is being subducted, melting, and then it says the molten rock often breaks through the surface near subduction zones to form volcanoes and eventually new mountain ranges. You see? So when that plate melts, it starts to rise. It starts to rise due to the convection currents, and it gets pushed up, and you create mountains and volcanoes. So volcanoes also occur over hot mantle spots that are far from the plate boundaries. A good example is found in Hawaii. This hot spot has existed for over 100 million years. The motion of the crustal plate during that time has allowed for the formation of 3,500 kilometers long chain of volcanic islands. So basically, as the crust is moving, there's a hot spot beneath it, which is welling up and creating the Hawaiian chain of islands. That's how we get Hawaii. So there is no subduction zone taking place in Hawaii. It's just that there's a hot spot underneath it and the plate is passing by it. Earthquakes are caused by friction between two adjacent plates and are a good way to mark the boundaries between tectonic plates. Earthquakes can occur both near subduction zones, near faults. Both are locations where two plates slide past one another. Okay. Occasionally, frictional forces will cause the plates to stick and halt the motion. Pressure will build up over time until suddenly the plates will rip free and resume their original motion. This sudden motion is what causes an earthquake. So it says here, the rubble and debris followed the 6.3 earthquake, which devastated the city of Christchurch, New Zealand on February 22, 2011. Pretty scary, man, when you look at the pictures. And that's only a 6.3. And we expect a bigger one to hit LA. So one way in which geologists express the intensity of an earthquake is with the familiar Richter scale. Each whole number increase in the Richter scale corresponds to a tenfold increase in the quake's amplitude. It is a logarithmic scale. Therefore, a magnitude 4 quake might cause small scale damage, while a magnitude 6 quake might cause widespread damage. Earthquakes of magnitude 8 or greater are rare but devastating. The map below shows relationships between plate boundaries and locations of volcanoes and earthquakes and the age of the seafloor. Use the show continents, show seafloor ages, shows volcanoes, and show plate boundaries, and show earthquake checkbox to view these features. So if I uncheck this, it doesn't show boundaries, but I could show the seafloor ages. You see, this is the newer age. This is the big rift zone in the Pacific Ocean. So you see, red means newer plates, newer boundary. And then this is these are newer boundaries too. Well, this is of the back, you can see right there. Blue is the oldest. So now show volcanoes. So if I undo the, okay, so then you can see here, you see where the volcanoes are? That tells you something about what's happening there. You see right there, right there. That's where the volcanoes are. Show plate boundaries. Ah, you see there? You can see what is happening here. Right there, a bunch of volcanoes here. So show earthquakes. Oh, wow. So a bunch of earthquakes here along the western coast. So we would expect earthquakes where plate boundaries are. So start. So again, this one, based on the Plate Tectonics Explorer, which is this one, which phenomena are associated with plate boundaries. So you can then take a picture here to support your answer. Which phenomena are associated with plate boundaries? So what you would do is keep the continents, and then one at a time, you would go like this, right? Maybe even get rid of the continents and then just go, okay, show plate boundaries and then show seafloor ages. So try to see, is there a correlation between seafloor ages and where the boundary of the plate is, like this. So take a picture of this then, just with these two checked. So see if there's a relationship, and then if there's a relationship, then put seafloor ages, right? Then uncheck this, and then show volcanoes, right? So you probably don't need the continents. It kind of gets in the way. So you're just comparing where the volcanoes are to the plate boundaries. Is there a relationship? So now take a picture of that. And then if there's a relationship, then you put volcanoes. And then which phenomena are associated with plate boundaries? Okay, then you do continents. Are continents associated with plate boundaries? So take a picture like that, and then answer if that's related. So then you put a check. And then the same thing, what's the other one? Earthquakes. So this is always checked for each picture, but we're only changing one thing at a time. That's why we're taking 4 pictures, because you don't want to have like this and confuse everything, you see? You want to have only one thing checked at a time. So now to see, is there a relationship? Then you go over here. So that's probably you're taking 1, 2, 3, 4 pictures, and then you're checking whichever one they're related. You're clicking submit, and you're then taking a picture of your answer, whether you are correct or not. Okay, as seen on the Plate Tectonics Explorer, 2 plates meet on the western border of South America. Which plate is being subducted? The plate on the east side of the boundary or the plate on the west side? That one you could actually, you don't need to take another picture, because you already got 4 pictures, one with plate boundary and earthquake showing. Then you have another one with plate boundary and volcanoes showing. So now you're focusing in on the I think the western border of South America, which is right here. Then decide, is this plate going underneath that plate, or that plate going underneath this plate? Right? And then so based off of that picture, essentially, you're basing it. So then make a decision which plate it is, whether a plate on the west side or the east side. Okay, then question 3. Japan is well known for having a large number of earthquakes. Which of the following best explains this phenomenon? So again, I believe you can base that on several of the pictures before. So you already have a picture of show plates and the continents. You might want to zoom in on those pictures, because it's a little bit unclear. So when you're taking the pictures, take it a big zoom, a little bit bigger. Where's Japan? I think it's this one, right? Like there. So now this just shows plate boundary and show continents. Then the other one will show plate boundary and show earthquakes. You see, then compare them, and then let's see if we show them together. Yeah, I see that Japan would actually be hidden behind this, you know. So yeah, Japan is this one right here. I'm pretty sure. I don't think it's that one. Yeah, it's this one. So then, based on those pictures, you can decide which of the answers and then show the picture here. So basically, that's going to be 4 pictures just from the first question. And then from there, you should be able to, then 3 pictures for each question. And I think we're left with the last portion. Let's see, where was I? I think we are done with that part, aren't we? Yeah, there's no arrow here. So then we're going to go to back to the planet geology. The last activity here. Comparative planetology. Oh, let me go to the first page. So they're going to compare the planets to each other. Because of the similarities in the way that terrestrial planets formed, we can use our knowledge of the Earth geology to learn about the geology of other planets. The planets in our solar system formed 4.6 billion years ago from a swirling disk of material known as the solar nebula. As the solar nebula cooled, gases condensed into solid grains of material that gradually combined into larger structures in a process known as accretion. So adjacent diagram lists many of the evolutionary processes that terrestrial planets and moons experience. So these ones here. Solid crust forms, heating and differentiation. Remember, differentiation means the denser material sinks, then crust forms, bombardment by the solar debris, volcanic flooding, some possibility of plate tectonics, solidification of the mantle, and then cold interior, geologically dead. Okay. Cooling. The interior of a small planet cools faster than those of larger planets. And this rate of cooling directly affects the interior structure of the planet. So smaller planets, it's saying, cool the faster. The interior of a small planet cools faster. So all of the terrestrial planets had a certain amount of heat energy at the time of their formation and have gained some additional energy because of the decay of radioactive elements. Both of these heat sources depend on the volume of material present, that is the size of the object. The surface area from which the object can cool also increases with size. However, as the size of an object increases, its volume grows more rapidly than its surface area, as can be seen by dragging the slider in the adjacent animation. So this is trying to show you that larger planets have a bigger volume to surface area ratio. So the volume determines how hot the planet was to start with. So such as Jupiter or what those gaseous planets, they were hotter. And then if you compare Earth and Mars, they were hotter than if you compare Earth and Venus, they were hotter than Mars and Mercury. So bigger planets are hotter to begin with. And then the surface area tells you how much heat the planet can radiate. But because bigger planets' volume grows larger than their surface area, they retain their heat longer, okay, than smaller planets. So let me get a little bit smaller. The lunar highlands were formed by meteor impacts, not plate tectonics. Because the moon is small, it cooled off quickly. Therefore, there is not enough heat to drive convection currents in the mantle. You see? So very small objects cool off very quickly. So no convection currents. There are two very distinct types of terrain on the moon. The light-colored areas known as highlands. They consist largely of low-density, light-colored rock. That would be this stuff right here. All this is the highlands, including this because it's just a crater right there. These are actually all the highlands right here. Okay. These materials rose to the surface of molten rock and solidified. The mountain ranges of the moon were formed by large impacts around 4 billion years ago. Large chunks of debris crashed into the moon at a high velocity and formed impact basins at the sites of the collisions. Mountains formed around the impact sites from the ejected debris. They are the rims of large craters like this one, you see. So these ones are kind of like mountains. The moon is equivalent to a mountain. And then this is the impact basin where the crater was formed. And also another crater here, and then all these smaller craters. This is a large one. This is another large one. The Maria, on the other hand, were formed by outflows of lava. This implies that at some point in the past, the interior of the moon was warmer than it is now. The dark areas of the moon are known as Maria, Latin for seas. These huge flat plains of hardened lava. Maria material is higher in density and much less reflective than that of the highlands. When lava flowed onto the surface of the moon 3 billion years ago, the low-lying basins produced by large impacts were filled in. However, the lava levels never reached the highlands. Oh, you see that? So the lava basically went up to the surface, flowed all the places where there were impact craters and all the lowlands, but they never reached way up to the highlands to cover all of the highlands. The distribution of the craters tells us a lot about the history of the moon. Note how the amount of cratering in the highlands is much greater than that in the Maria. So these are the Maria right here, the dark spots. Well, there's a lot more craters on the highlands right here than in the Maria. So that tells us that the Maria formed after the cratering and then came and filled up that region, you see. So if I show you another images of the moon, you could see Maria on the moon. You see there? Those are all the Maria right there. That's a nice image. You see here? That's a Maria right there. That's Maria right there. Mare, it's in Latin is mare. See, this is another one. Oh, see, the Maria, interestingly, are only found on the side of the moon facing us. You see here, these are all the Maria right here. They're denser and they are filling up the lower regions of the lower basins of the moon. And they don't have as much craters, you see, as the highlands. These are all the highlands right here. Okay. Mercury. Like the moon, Mercury is small, and therefore it is unsurprising that both bodies share similar surface features. Both also possess iron cores, both the Mercury and the moon. Mercury is very similar to the moon in that it has both extensive cratering and Maria. So the Mercury does have both. It also cooled rapidly due to its small size. Mercury's rapid cooling gave rise to some very interesting geologic features known as lobate scarps. These are giant curved cliffs as high as 3 kilometers and stretching for hundreds of kilometers. So there are 3 kilometers is actually pretty high. That's like 1 mile, 1.5 miles. So that's about a good 7,000 feet. That's how high the lobate scarp is. They form when Mercury's crust wrinkled because of rapid cooling, much like the drying out of a raisin. Or scarp and cratering on Mercury. This is the lobate scarp right here. I believe right here, all of this, you see, one side of it is higher than the other side by about 3 kilometers. You see, so we can see here lobate scarp on Mercury. So several pictures of it, you see here. Now, we can't tell that one side of it is that much higher than the other because we're looking at it from the top. But if we go on the surface and take a picture, this side will appear a mountain like 1.5 miles higher than this, you see. Yeah, those are some good pictures there, you see, like that. Probably the moon has some too, but maybe not as extensive. Yeah, there are some. Yeah, right there. This is for the moon. Yeah, right there. Okay. So it says, although the Earth has the highest density, remember it was 5.5, this was achieved over time through gravitational compression. The Earth's uncompressed density would be about 4 grams per cubic centimeter. Remember the fact that you compress it something that also tends to increase its density because you're squishing it into a smaller size. So if the Earth wasn't compressed due to its gravity, it would have a density of 4 grams per cubic centimeter. Mercury's density is 5.3, has been achieved with very little compression, and likely implies a large iron core. Okay, so Mercury's density is more pure density without compression, because since it's small, it doesn't have as much gravity as the Earth, so it's not being compressed due to gravity as much. So the fact that Mercury's density is 5.3 is more real, the density. That means you wouldn't want a planet like that impacting you. It's pretty much made of a lot of solid iron in there, Mercury. That's why it has that density. So if we were to compare the uncompressed density of Mercury to the Earth, Mercury would be higher. The Mariner 10 spacecraft detected a magnetic field when it flew by Mercury. Although 200 times weaker than the Earth's magnetic field, Mercury is stronger than any other terrestrial planet's magnetic field. That's interesting. Even though it doesn't have a molten core inside, it doesn't have a liquid core, but because it has iron core so big, that is still enough to create the second strongest magnetic field from the terrestrial planets. Okay, now we go to Mars. Mars shows evidence of volcanism, but not plate tectonics. So it does have a lot of volcanoes, but not plate tectonics. Its medium size allowed it to retain heat longer than the moon or Mercury, but not as long as the Earth or Venus. The degree to which Mars retained its heat is reflected in its surface features. Mars is intermediate in size between Moon and Mercury and Earth and Venus. One would therefore expect Mars to have been internally active for an intermediate length of time. Olympus Mons is the largest mountain in the solar system. This is a view of the Olympus Mons from the top. Look at it. It looks like as big as Arizona. That is huge mountain. So there's considerable evidence of past volcanic activity on Mars, but evidence of recent activity can be seen only in the Tharsis region. where there are huge volcanoes. These are all shield volcanoes created by hotspots poking through the crust. So kind of like the one that we called Hawaii. Hawaii is also an example of a shield volcanoes coming from the hotspots. On Earth, the crustal plates don't stop moving long enough to allow a real large volcano to grow. Remember how they keep moving? That's why you get the formation of the Hawaiian Islands, right? But on Mars, the crust doesn't move. So a hotspot keeps creating a mountain. That's why you get a mountain like Olympus Mons in the same spot. It's the largest mountain in the solar system. So it says Olympus Mons indicates that it has been active within the last 200 million years. Although volcanic activity has never been observed on Mars, there's no reason to assume that it won't occur again in the Tharsis region. Now on to Venus. Like the Earth's surface, Venus's surface shows volcanic activity and renewal. So that means we'll keep seeing more volcanic activity on Venus, whereas in Mars, not as much. But in the past, there has been. Interestingly enough, however, the planet does not show evidence of plate tectonics. This lack of plate tectonics could be due to the differences in the two planets' development and atmospheres. Most of what we know about Venus comes from the Magellan space probe, which created radar maps of almost the entire surface. So Venus, very few impact craters are found on Venus. It appears that all crater evidence was erased about 500 million years ago in volcanic resurfacing. It's kind of how the Earth rejuvenates its crust. Similar thing is happening on Venus, but without plate tectonics. The volcanoes, eruptions, the lava flow is just covering up the cratering, so you don't really see it. So all the craters, about half of them, it appears that all crater evidence was erased about 500 million years ago. Most of the interior suggests that every couple 100 million years, Venus may undergo brief periods of intense volcanic activity. Venus has more than 500 volcanoes with diameters greater than 20 kilometers. That's a lot. So Venus shows no evidence of crusts broken into plates. In fact, the crust motion appears to be largely vertical. Oh, okay, so the crust goes up and down, but not sideways. Okay, start. Sort the properties into the correct field. Properties of Mercury only, then you could just sort them here. Shared properties of Mercury and the moon. And then you could put those over here. And then that one is just pretty much just doing it. So then question 2, let's know why Mars has giant volcano like Olympus Mons. Okay, that one you can just take a picture of your final score. So it's not really based on anything that you do on top here. So just answer this, hit submit question 2, and then hit submit. And then once you press next, it shows the score. And that's all you need for that one. Just show the score, how many you got. I think that's it. Very interesting stuff. So even though this section didn't have much exercise on it, but I still usually like to read this section because we're learning things as we're going along. And that might be also helpful for future labs and overall in your astronomy knowledge. As well, too, when you're doing the discussions about the labs, you can include things that you learned while I was lecturing. Not necessarily something you did as an activity, but you learned something that I mentioned or something that I showed you, and then something that you learned as you read these paragraphs. So also mention those things in your discussions about the labs, not only the exercises that you did. Or you could even mention things that you learned when you were doing these questions, you know, things that you learned as you were answering them. So that all can go in your discussion answers, not just the mathematical questions, but the concepts that you've been learning. So put all that stuff in the discussion. Okay, I think that's it. So have a good day. This video will be posted soon today. Mm-hmm.